Okay, and we should be live. Let me just check everything is working all good. Let me just check my mic. That's working, but then is that working? Let me just check. Get some feedback. Let's have a look. Do that. Turn that down though. Has that's working, but is the video working? Let me just try. Type in keyboard, it should be fine now. Yeah, that's much more quieter. That's much better. Okay. Right. Let's continue then. So we left off. We left off at debugging, and we did step in and step. Let me turn that down, and let me turn this down. Okay, I think I shouldn't get any feedback now, or whatever it's called, the one where I can hear myself talk. Anyway, yeah. So last stream yesterday we did debugging, and we did step in, step out, and then we did step over, I believe. And we're going to start today with running and breakpoints. Yeah. So when stepping, like last time, we used here, what we did was we ran the debugger, and then we had the option to, we need to type in password. And then what we could do was we could run the debugger. We could, sorry, okay, yeah. We could run the debugger. And then we had the option to step over, which stepped over everything, step into, which would go from main to print value, and then you could do step out, which would step out of the main. Okay, that's sorted. Now what we'll do is we will we shall okay, yeah, we shall what should we do? We shall continue with debugging in the sense of breakpoints. So modern debuggers often provide useful tools to debug even further. Yeah, so we also learned that we could do something like std cer print current error, and then we would do main is running with a line break, and then we could also do std current error, and then we could do main as ran print value. However, whilst that may be good, the fact that we're having to type in every single line to try and find the issue can take time, and it can also be annoying. That's why we use the debugger tool. But we'll just run the code instead of debugging it. Run. I want to run instead of debug. Yeah. So you can see here the run is the main is running 5. Main has printed value, and we could also do here std current error print value is running in print value is running, and then we can do a new line, and then we can do std current error print value print value has finished running. And then what I would do actually is I'd change this to main has ran. So we run that. So we got main is running, and then obviously it goes to print value. We then go up to print value. We then see that print value is running. We then get the value of 5 because that's what we passed in as the argument. And then print value has finished running. And then once print value has finished running, our main has finished running. That is an option. However, as we discussed last time, it can be quite repetitive to do that on every single line. But it is still a tool that we can use, and always a good one. Okay, so now we'll do running and breakpoints. The first useful command is commonly called run to cursor. The run to cursor command executes the program until extraction reaches the statement selected by your cursor. This then returns so you can debug starting at this point. This makes it an efficient way to start debugging at a particular point in your code. Okay, at a particular point in your code. Or if you're already debugging, you can move straight to some point you want to examine further. So in VisualCode, you can run to the cursor command. It can be accessed. Sorry, that's Visual Studio. We're using VS Code. And if you're using Visual Studio and you're following along, just go along with this. Or if you're using code blocks and you're following along, you can just go along with this. Okay. For VS Code users, the run command to the cursor can be accessed while already debugging by right-clicking a statement on your code and choosing run to cursor. So let's give that a go. I'll get rid of these current errors. Actually, I'll just comment them out for now. So we can do it by, as he said, debug the file. So we're successfully running the debug and right-clicking a statement in your code and saying run to cursor. Could it be in run? So are we actually debugging? No, we're not yet. But we're debugging now. And then we're right clicking. And we should find we can have a run to cursor. We got refactor. Run code analysis. Run to cursor. Okay. Simply click. Okay. No. We'll run the debugger again. We'll click line 5. All we need to do is double click. I don't think we need to highlight. We then go down here. We run to cursor. And that just selects. Okay. And then as you saw, it jumped from here to line 5. You'll notice that this program starts running and execute the line you just made. If you run to cursor to a location doesn't execute, your run to cursor will simply run your program until termination. Okay, continue. So does that mean you run the debugger, and then what if you did run to cursor here? Okay. So continue. Once you're in the middle of a debugging session, you may want to just run the program from that point forward. The easiest way to do that is use the continue command. The continue debug command simply continues running the program as per normal, either until the program terminates or until something triggers control to return back again. So VSCode. In VSCode, with the continue command can be accessed via the debug program run menu continue. Okay, let's stop that there. And then we'll run the debugger. And then we'll go up to our run. And then we'll continue. So once you're in the middle of a debugging session, you may want to run the program from that point forward. Okay, so it just continues from the normal. Start. The continue command has a twin brother named start. This command but surely if you just did that, yeah, see, I don't know if you can see on the screen, but when you hover over the run and debug, you just get a start debugging F5. And if you use a start command, because we set, yes, because last lesson, we did launch JSON and we had this stop at entry. By default, the configuration is false, so we changed it to true, allowing us to run the debugger. And if you'd like to see how to do that, I recommend watching the last stream. Breakpoints. The last topic we're going to talk about in this section is breakpoints. Breakpoints are a special marker that tell the debugger to stop execution of the program at a breakpoint when running the code. In the VS Code runtime. Yes, you can also do this. Click to add a breakpoint, and then we run to debug. And then as you can see, we only get here. You don't necessarily have to do that. You can just click here, and here we see we run a breakpoint anyway. Now choose the start command, and as you can see, we only get here. Yeah, so for example, if we set a breakpoint here, we should only run to here. He says, okay, so you can't, you have to put the breakpoint on a statement. You can't put it on the braces. Okay, get rid of that. So if you put the breakpoint here and run the debugger, you'll see that our debugging session, and we actually run it. Go on, run it. You should find that. Why is it not stopping? Oh, because you're running multiple debuggers, that's why. If we run it again, paused on step, yeah, so we saw that worked. If you just run the cursor to the point, it's just as if you'd run the cursor to this point. Breakpoints have a couple of advantages over the run to cursor. First, a breakpoint will cause the debugger to return control to your entry every time they are encountered. Second, you can set a breakpoint and it will persist until you remove it. Okay. So yeah. Where were we? Note that the will persist until you remove it, whereas run to cursor will have to locate the spot you run each time you run the command. Yes, that makes sense. Note that the breakpoint places on lines are paths are not the path of execution, will cause the debugger to halt the execution of the code. Let's look at our slightly modified program that better illustrates the difference between breakpoints and run to cursor. So we got a preprocessor directive of include, we got IOStream, we got a return value of void, we got print value of a parameter of value, we got SCD character output value, and then line break. We got a return type of main, and we're printing the values of 5, 6, 7. First, start a new debugging session and run line to the cursor to line 5. Now choose continue. The program will continue to the end. It won't stop on line 5 again through line 5. So let's give that a go. So void print value int value std character output value and then a line break. Then what we'll do is we'll have a main where we print the value of 5, print the value of 6, and then print the value of 7. And then we return 0. So if we start a new debugging session, uh, start a new debugging session, and then we run to cursor, so run to cursor on line 5. If we run to cursor on line 5, run to cursor, now we press continue. Yes, it goes all the way through. Okay, I get the hang of that. I think I can then move on from that. So what we'll do now is we will let's do set next statement. Not conclusion. Okay. Where's set next statement? Where were we? Breakpoints. Set next statement. There is one more debugging command used fairly uncommonly. But it's at least worth knowing. What I think I'll also do is I will, so I'll close that, for the various in IDE debugging abilities, go to lesson 3.7. The set next statement, just because I don't really feel like fancy copying all of this. Okay. The set command allows us to change the point of execution to some other statement, sometimes informally called jumping. This can be used to jump from point of execution forwards and skip code that would otherwise execute, or backwards, and have something that already execute again. In your VS Code, you can jump to a point of execution by clicking on the statement and choosing Jump to Cursor from the context menu. This is optional in this option is contextually and only occurs when already debugging a program. Run to cursor to line 11. That's right, because we need to start a new debugging session. So we start a new debugging session, line 11, run to cursor. Oh, sorry, right clicking on the statement and choosing, yeah. First run cursor to 11 and you should see the value now. Now choose line 12 and set next statement. Am I choosing jump to cursor. That's what I did. Oh, jump to cursor. Okay. It seems to be working, but since it's uncommonly used, I'll leave that for now. So now right-click line 12 and choose next statement. This one. Okay, yeah, that makes sense. The next statement command will change at point of execution, but will not otherwise change the state of the program. Your variables will retain whatever values they had before the jump. As a result, jumping may cause the program to produce different values, results, or behaviors. You should not use set statements to change the point of execution to a different function. This may result in undefined behavior and a crash. Step back. Yeah, because I thought surely a step back would be better. Step back rewinds the state of everything as if you've never gone past it, whereas step next, when used to jump backwards, only changes the point of execution. Okay. You've now learned, conclusion. So now we'll move on to watching variables. Okay, so we've got a decent amount. Watching variables. Right. Okay, just give me a second. Yeah, okay, we're still good. Yeah. Apologies, give me a sec. Okay, right, let's actually focus. Using an integrated debugger, watching variables. Watching a variable is a process of inspecting the value of a variable while the program is executing the debug mode. Most debuggers provide several ways to do this. So let's copy the program. So we want to include the library of IOStream. We want an integer of main. We then will do int1 and initialize it as 1, int x and initialize it as 1, and just make it easier to read. We'll do a character output of x, and then single strings, and then we'll do x equals x plus 2, and then we'll do standard character output of x, and then again 2 single strings, and then we'll do x equals x plus 3, and then we'll do a output of x, and then single strings again. And we'll finish off as always with a return of 0. And then we'll run that, we won't debug it, and you can see we get 1, 3, and 6 because we had 1 set as a variable, and then we did 1 plus 2 is 3, and then we carried on the 3 for 1 plus, 2 plus 3. No, sorry. This is 3. 3 plus 3 is 6. First, run line to cursor at line 6. So we'll debug the file. We will then run line to cursor. At this point, the variable x has been created and initialized with a value of 1, so we need to examine the value of x. We should expect to see a value of 1. The easiest example of a simple variable like x is to hover over your mouse to see the variable of x. Some modern debuggers support this. 1. Okay. So as of that point, x is 1. Note you can hover over x on the current file, for example. Yeah, so if we hover over the value in value 12, we still get 1 because we're running to cursor here, and our local variable is still 1. So we can right click. Does Visual Studio VSCode have a quick watch? No, it does not. Maybe that's because now let's change the variable. So we'll then run to cursor here to std character output at line 9, and we should hover over x and we should get 3. We do. Okay, that makes sense. It does. I think I'll use the mouse hover rather than quick watch. So we can use a window, we can use the hover. Yeah, so it's gone from, okay, so, but it only shows you the value at that line. In order to address this issue, the watch window is a watch x. Oh yeah, so typed in x and we get 3. Okay, that makes sense. Pull up the watch window and type the name of the variable we'd like to see, as I did there. In the code window, right click. In the code window, right click the variable you want to watch. And choose Add Watch. Add to watch. Yeah. And run to cursor. So we'll actually stop that. We'll close that. We'll run to cursor. We'll set a new debugging one. We will then run to cursor and we get 6. Okay, cool. And you see we get the register of 6 here. So then what we want to do is we want to now step over twice. Variables that go out of scope will stay in the watch window, but will generally either be marked as not available or not shown, or show that the value is grayed out. If the variable returns the scope, the function is called again. Its value will be shown again. Therefore, it's fine to leave variables to watch window, even if they're out of scope. If you feel like I'm going too fast over this, you can always go to the debug lessons in this, but the whole purpose of these streams is so I can learn C++. So that's why I'm not going as much into detail, but obviously still debugging is a very important skill and very important for coding. Just because I'm not going over it in detail doesn't mean I don't think that debugging is not important. Just to let you know. Using watches is the best way. Setting a breakpoint on watch variables. Some debuggers will allow you to set a breakpoint. This will cause a program to stop, as we learnt there, and a breakpoint can be done by just clicking on the line you want to break at. So I think I'll go over that because I would rather get to types, and I obviously, me skipping over these bits doesn't mean that debugging is not important, but I personally want to, I have some experience in debugging, maybe not as much with the tools, but I know roughly how to debug. So what I'll do is I'll skip over, not entirely, but I will not cover this as much in detail. Okay. Modern debuggers contain one more debugging information window that can be very useful. The stack, the call stack here. Whether your program calls a function, how do you know where to return to? The answer is in the call stack. The call stack is a list of active functions that have been called to get to the current point of execution. The call stack includes each function that is called. Whenever a new function is called, it's added to the top. The call stack is a debugger window that shows the current call stack. If you don't see it, you'll need to tell your IDE to show it. I have it here. So let's look at the simple program. So again, we'll call the include library iostream, and then we'll do void a, which has a character output of a is called, and because it's void, we don't actually need a return type. Void b, std character output, b is called, will be calling A within B. And then again, because it's void, we don't need a return type. In our main, with a return type of integer, we will call A and we will call B, and then a return of 0. So the main semicolon, the main will call A first, then it will call B, and B calls this, B outputs this, and then calls A. And then calls A. So you'll get A, B is called, and then, you'll get A is called, then we'll get B is called, then we'll get A is called again. Put a breakpoint on line 5 and line 10. And you can see here also we have breakpoints being checked here. Because the function A is called first, the breakpoint on line 5 will be hit first. At this point, you should see something like this. So what I'll actually do is, I'll debug it again. And you can see actually it's not in the call stack, it's actually in the breakpoints. But as you can see here, the difference is inconsequential. What's relevant is the 2 top lines from top to bottom. Now choose continue debug. Hang on a minute. Where was my continue? Continue. And then we'll continue again. And you can see, yeah, okay, good. There, B becomes the top, like we have here. Cool, nice. Choose continue to debug one more time. And we'll hit the breakpoint on line 5, i.e. when A is called again. So we'll continue. And then we get line 5 again. Cool. Line 5 in here, and line 5 in my call stack here. Cool. That all makes sense. Nice. So now we'll move on to the next lesson. And we will finding issues before they become problems. Okay. So, when you make a semantic error, the error may or may not be immediately noticeable. An issue may lurk undetected in your code for a long time before newly introduced code or changed circumstances cause to manifest a program malfunction. The longer the error sits in the code base, the more likely it is to be difficult to be found. So what can we do? Don't make errors, obviously. Follow best practices. Don't program when tired or frustrated. Like, for example, driving a car, you don't want to do that. Take a break and come back later. Yeah, I found that sometimes if I'm on a task of something in particular and I'm struggling a bit with it, the best way is to just move on from it entirely, and then um, go on to something else completely different, just to distract your mind, and then maybe take a day or two to work on something else. Come back to it, and often you'll see, oh, it's so obvious. It was because of this. Let me just stop the debugger because I just saw that was continue running. I'll get rid of these breakpoints. Understand where the common pitfalls are in language. Don't let your functions get too long. Prefer standard library to writing your own code. Comment your code like saying, what does this do? What does that do? Start with simple solutions. Avoid clever, non-obvious solutions, and optimize readability. Refactoring your code. As you add new capabilities to your program, behavioral changes, you can find some of your functions grow in length. As functions get longer and longer, they become harder to understand. One way is to refactor. Refactoring is making your program less complex. So how long is too long of a function? If you have to scroll to read, it's probably too long. Ideally, the function should be less than 10 lines. A bit iffy on that, because you could have a function that calls a function that calls other functions. And sometimes if it's like, if the calling of the functions end up being 10 lines, i.e. you call 10 functions within a function, but each function is quite small, I'm at the moment of the opinion that you don't need to call all these functions. You can just write it in one, but we'll see as I progress. Remember, it's to maximize comprehension, not maximize function length. Abandoning best practices or using obscure code doesn't do you any favor. Defensive programming. Errors can not be making, but also occur when using the application. Did not anticipate. For example, if you ask the user to enter an integer and instead they enter a letter, how does your program behave? Unless it's anticipated, error handling the case, probably not very well. Defensive program, whereby the programmer tries to anticipate the way software could be misused, either by end user or other developers. These misuses can be detected and then mitigated. We'll explore these topics and in future lessons. Finding errors fast. In testing functions. One common way to help uncover issues in your program is writing functions to exercise the code you've written. Here is a primitive attempt for illustrating these purposes, illustrating this. So we got a return type of int add, and we're returning the parameters x and y by adding them together. We're testing add. This function should print 2, 0, 0, minus 2. Okay, so yeah, because 1 plus 1 is 2, minus 1 plus 1 is 0, 1 minus 1 is 0, and minus 1 minus 1 is minus 2. This test add function is this test function adds the test function by calling different values. It's called unit testing. Okay, makes sense. As with logging frameworks, there are many third parties. Yeah, okay, that made sense. I'm not going to bother running this because to me it's fairly straightforward. If you'd like to run it yourself, obviously feel free to do so. But I am personally at the moment not going to do that. Introduction to constraints. Constraint-based techniques to check that some set assumptions are not violated. For example, if we were writing a function to calculate the factorial of a number, if the caller passes in a negative number, the function could immediately error. Yeah, so we'll cover that in a later lesson. Shotgunning the general issue. Programmers tend to make certain kinds of mistakes, common mistakes, sorry. These programs generally known as static analysis tools, sometimes called linters, of programs that analyze your source code to identify semantic errors. The issue is found by static. Okay. You already have one static tool at your disposal, your compiler. Okay. Programming errors. Okay. So third-party libraries, basically. Use static tools to help you find. Okay. Cool. Let's move on to chapter 3 analysis. And again, I know last time when we finished functions, I did the summary in here. Oh no, I didn't. But if you just want to, have a summary and a quiz, it's always the end of each chapter. What I'll do is here, I'll go down and I'll change this to debugging and chapter 3 summary on learncpp.com. Okay, where are we now? Yeah, a syntax error is an error that occurs when you write a statement that is not valid and not correct grammar. The compiler will catch it. Semantic error occurs when a system is syntactically valid but does not do what the programmer intended. The process of removing errors is debugging, and then we did that the 5-step process, but I thought there was 6. Yeah, there was. Debugging generally involves 6. Debugging. Find the root cause, yeah. Understand the problem. Determine the fix. Repair the issue. Retest. Okay, so the 6th step is not included here, but once you've fixed one issue, often you'll find that there is other issues because your code runs sequentially. Your code runs sequentially, so so if you have an error here, it will not go past that line of code. But if you have an error here and you actually had an error here, once you fix this error here, your line of code will run to here and we'll get an error here. So that would be the sixth step. Finding an error is the hardest part of debugging. Static tools are used, such as IDEs. That makes sense. Being able to reproduce an issue in the comment out code. Remember, with commenting code, you can either do this, or if you want to comment out a bunch of code, you can do the if zero. So if zero, and then your code some code here. I'll do snakeskin, and then once your code is finished, you'll need to do end if. And then if you want to uncomment that code, you just do if one. Yeah, I covered that in the previous streams, so feel free to check that out if you really want more detail for that. Okay. Yeah, as covered a few minutes ago, we can use standard std character error instead of character output. But we can also use the actual debugger installed in most IDEs. A log file. Process of log file is logging. Process of restructuring code is refactoring, i.e. chopping up your functions into smaller functions and then putting it in that function that you had. Oh, no, not yet. Almost. Be right back. Yeah, still good. The process of restructuring is refactoring. Unit testing is software testing method. Unit. Defensive program, anticipating the errors, anticipating how software could be misused. A debugger is a tool in IDEs. An integrated debugger is within the IDE, for example, via Xcode or VSCode. Stepping is the name for related to debugging features that allows you to step through each statement. Step into executes the next statement. Step over executes the next statement in the normal execution path. Step out executes all remaining code in the function. Run to cursor executes the program until execution reaches the statement selected by the mouse cursor. Continue runs the program until it's terminated or hits a breakpoint. Start is the same as continue. A breakpoint, which is this, is a special marker that tells the debugger of the program when the breakpoint is reached. Set next statement is a command that changes the point of execution to the other statement. Watching a variable, as we had in here, allows you to inspect the variable when executing a debug. A call stack is a list of functions that were executed, and the call stack window is here. We also have the breakpoint window, but because we haven't selected any breakpoints, it will not appear. Quiz time. Right, okay. How many questions are there? Okay, 4. So we'll do these 4 questions and then we'll take a little break. The following program is supposed to add 2 numbers but doesn't work correctly. Use the integrated debugger to step through the program and watch the value of x. based on the information you learn, fix a program. So let's just check what it actually runs. Actually, we're on the hour point, so what I'll actually do is I'll take a break right now, and we'll come back to this, and we will do those questions. Okay. Okay, and we're back. We still good on the sound? Hello. Yeah, good. Okay, let's finish off debugging then. Right. So let's do this code, include input output string. We got a return type of integer and we have a read number with a parameter of integer x. And then we are asking the user to enter a number. And then we are providing the opportunity for them to enter the number. But one thing I can immediately see is we're not actually setting the variable. So we return x, although we're setting it here actually. So potentially I'm wrong. So void write answer integer of x, and then standard character output. The sum is x with a line break. And then because it's obviously void, we do not need to return a value. I just need to put my laptop on charge. Just give me a sec. Cool. That's on charge now. Okay. And then we have the integer of main. Sorry, the function main with a return type of integer. And then we're going to set int to be unassigned, uninitialized, and then read number x, and then x equals x plus read number. And then we will write answer x. And then we'll return 0. So let's just run that first and see what actually happens. So I want to close that, clear my terminal. I'll run it rather than debug it. So enter a number 5, enter a number 5. The sum of 5 is 5. So we're not actually adding them together. So using to step through the program to find the value, to watch the value of x. So we're going to be using watch call, and then we're going to want to watch x, and then we will want to step through the program. So we'll start debugging. We'll step into, so x is 0, so x is 0, sorry, So we're watching X, but as you can see here, X is, I think that means X is undefined, an undefined error. So, and step through the program. So we'll step through, so we'll step into X is then 0, X is 0, X is 0, X is not available, because we should be defining X as a variable here. So if we did int X and then we return X, would that work? No, because then we have the read number being X. So read number is, so then we get rid of this line. No, that's not correct. Surely, what about if we did that and then we ran it rather than debug it? No. Redeclaration of X. Is that because it needs to be above this? We got a redeclaration of X. No, so that's not the issue. Um, hmm. So we're not adding. So surely we need to do this, no? Read number, and then we run it, and then we get 1 plus 1 is 2. Okay. But I am not entirely sure as to the specific reason as to why that now works. I know what I need to do, but I'm not really sure how watch helped me there. Is it because it was undefined here? 0, 0, 0, unavailable. The major issue is the second line in the function main. Okay, so we could have just put read number in main. Okay, that makes sense. The following program is supposed to divide two numbers but doesn't work correctly. Use the integrated debugger to step through for inputs. Enter 8 and 4 based on the information you learned to fix the program. So we got the read number, we got integer x, writing answer, we've got x and y being unassigned, x read number, x read number. But then y is 0, so you just need to make that y, isn't it? Yeah. And then put the read numbers in there to save lines. Okay, that does make sense. So you would, obviously it's not the same question, but you would do x. Question 3, the call stack. The call stack is a point of execution on line 4. What does the call stack look like for the following program at the point of execution on line 4? Only the function names are needed for this exercise, not the line numbers at the point of return. So what does the call stack, i.e. So what does the call stack look like? I.e. what functions are we calling? So include IOStream, and then void D, it's just an empty body. Void C is an empty body as well. Void B will be calling C and D, where we need brackets. Then void A will be calling B, and then we have a main function. We have a main function of A with a return type of 0. Okay, with a return type of 0. So what does the call stack look like? We'll run it, debugger, get rid of that. Point of execution, only the function's name are needed. So what does the call stack look like here? Which I believe is F5. Or is it run the cursor? So main D, main B, main A, main. Is that what he was looking for? Yeah, D, B, A, main. So we're in main, which calls A, and A calls B, and no, we're running D, which means the call stack is calling D, and then we're running B and we're running A, and then we're calling main. Question 4, extra credit. The following program is supposed to add two numbers, but it doesn't work correctly. But doesn't work correctly. Just give me a second. I'm not looking at the answers, don't worry. I'm just checking something. Okay. Use integrated debugger. So we got a read number. We'll stop that for a second. We'll get rid of the breakpoint. We'll delete this code. We got a return type of read number, and then character output of please enter a number. And then oh, there we go, immediately. We got a character of an X, which is a character, not an integer. And then we're allowing the user to input their answer of X. And we will be returning X. And then in our void right answer, int X, we will be producing the character output of the sum is, and then X, and then a new line break. And then we will be returning main. And then we will be int X, read number. And int Y read number. And then returning, and then returning 0. Okay, so use integrated debugger to step through the program for inputs. For inputs, enter 8 and 4. Use the integrated debugger. And obviously the error is with char, but I'm not entirely sure about the how to use the integrated debugger. Obviously this is something I need to work on. So it would just be changing integer, right? Yeah. Yeah. So that was obviously the issue, but I'm not entirely sure about how to fix that. So I think debugging might be a bit more work might need to be going into that. So perhaps that might be something I do off stream. So because obviously this is a fairly simple program, I spotted the difference right away. But when my program gets a bit more complicated, I might need to work on that a bit. Okay, so it looks like now you're still having errors. Really? Because we're not writing the answers. That's why. I never entered um, x plus y. So now when we run it, we still get an issue. Read number in duplicate symbols. You got a standard character output. You changed x to that. You returned x. You've written the answer. Int y, right answer x plus y. Sorry, what am I missing here? Integer read number, standard character output. Clear the terminal. You got an integer of x reading the number. And then you got an integer of y also reading the number. And then you got right answer x plus y. I'm clearly doing something wrong. Have I got a read number somewhere else in my file? Yes, I do. You got a read number in. Okay, so what we'll do is we'll just do read num. I got something from previous file. So read num. Now if we run it, yeah, good. 2 plus 2 is 4. Cool. So I'm glad that's fixed. Okay, so it looks like we've finished debugging. So what we'll do now is we will move on to data types, but first we will store it in our Git repository. So what are we now on? Day 6, are we? Let me just check what day we're on. Yeah, we're day 6. Okay. Day 6. So day 6, part 1. What did we do? We finished off learning about debugging, and we did stepping, run to cursor, continue. We did break points, and I think that was it. Let's just go back to it. Watching variables as well. We also did the core stack and breakpoints I've already done, and the importance of defensive code. Cool. Tutto bene. And the date today is the 3rd of August, 2026. Cool. Just gonna This is gum, not anything else. We get any ideas? Okay. I'm just going to take a break here. Okay. And we're back. Okay, sorry about that. Okay, right. Let's continue. Uh, oh, okay. So where were we? We are now doing data types. Yeah. So do is to avoid that potential number or duplication um, duplication glitch. We will delete some of these files. Oh no, but they're commented out. Let's just comment them out actually instead of deleting them because they're always good reference to come back to. Okay, so fundamental data types. So we'll scroll up to here. We'll do chapter 8. Fundamental data types. And we'll scroll down to the bottom. And then we'll do chapter 8, fundamental data types. Okay. Introduction to fundamental data types. Let's go. Bytes, bytes, and memorizing. Bits, bytes, and memory accessing. So if you didn't already know, the random access memory RAM is available for programs to use within a computer. And allow us to access certain memory. Memory is organized in something called a memory address or addresses, similar to how you would have a house on a street. In C++, we typically work with data-sized, bite-sized chunks of data. I did not know that, so I'm going to do that. We'll get rid of that. Okay. The following picture shows some sequential memory address along with corresponding data. Is that what SQL stands for? The sequential query log? I know it's not C++, but I've never actually dealt with SQL. So what does SQL stand for? In programming. Oh, SQL. Structured. No, okay, so it doesn't. So we got address. That's really annoying. Okay, good, it stopped. Address 0, aka index 0, index 1, 2, 3. And this is in binary language. I can't read binary language, but it's ones and zeros. Because all data on a computer is just sequences and bits, we use data type. We often call it a type for short to tell the compiler how to interpret the contents memory. Yeah, as we covered, as they said in lesson 1.3. when you give an object a value, the compiler and the CPU takes care of encoding. For example, you assign an integer the object value of 65. This value is converted to the sequence bits 10000010 and is stored in the memory. I believe that's how you read binary from right to left. So it's read, it's scanned. Again, it's AI, man. I asked if it's read, but then it says it's written. Ridiculous. But mathematical value is calculated right, so i.e. on the right side, to left. I asked if it's read, and then it asked me for written. Stupid. Anyway, so it's read like this. But obviously we don't need to do that because we have compilers. All you need to do is pick the data type you desire. The fundamental data types are, as we've covered previously, float, double, which are basically the same things, long double, which I've never come across of. Maybe that just means a really long decimal point number. Boolean, true or false, character, all these other subsets, short integer, int, long int, long int, std, null, print, a null pointer, and a void type. What I will do is I will make a screenshot of that for future reference. The character is this character is dedicated to explore this character chapter is dedicated to exploring the fundamental data types in detail, excluding this, which we will discuss when we talk about pointers. So, integer versus integral types. Integral. In maths, an integer is a whole number. The term integral has several meanings, but the context it means like an integer. Okay. So you got a standard integer type of short, int, long, long. Short, int, long, included the signed, singed. Yeah, singed. Integral types are booleans, various char types, and standard. Okay. All integral types are stored in memory as integer values. Okay. Also, no integral types. Yeah, so enums are basically things where you can assign values to certain things. I've done some of that in Swift before, but I assume we'll cover it later in C++ because Swift is obviously derived directly from C, and C++ is directly from C, and obviously Swift is in Objective-C, so it all links together. But I assume we'll be covering enums later. Other set types. C++ contains 3 set types. Contains 3 set types. The first 2 are built in into the language itself and do not require the inclusion of a header. Okay. And then I'll copy those are the fundamental types, and then the command data types. The fundamental types provide the most basic and essential type datas. Compound data types provide more complex data types that allow for creation of custom user definition. I assume that is things like structs and classes and enums and switches. The distinction isn't interesting or relevant, so we'll go over it. The third is provided by a standard library. Okay. Nomenclature, built-in types. Are part of the standard library. So we'll be covering strings in the next chapter. Introduction to STD strings. So the T underscore T suffix. Type. Okay. So it seems these fundamentals is going to be more about reading rather than actually practicing with code. So void is the easiest data type to explain. Void means no type. Like if you're void of emotion, you have no emotion. Okay. Incomplete types cannot be instantiated. Won't work. Variables cannot be defined with void. Okay. Variables cannot be defined with the incomplete type of void. Okay. Functions that do not return value. Yes. The uses for void include functions, as we've learned previously, that do not return a value. As we've done previously, for example, the return type void, the return value with a parameter of int x, and then a character output of the value of x is x. No return statement because we have a void. And as we've learned in previous streams and previous lessons, if you try to run it, you will get a compile error. deprecated. Okay. So we can use void as a parameter. Even in functions that have non-void non-void return types, such as, so your int get value, and we pass in the parameter of void, and then we have a unassigned variable of x, and we ask the user to enter x, and we return x. Although this will compile in C++, the use of the keyword is considered deprecated in C++. Okay. However, the use of void is considered deprecated, and therefore just leave the parameters as empty. Use empty parameters instead of void. We'll cover in void pointers. Let's move on. Okay. Object sizes and size of operator. As you learn, we can use size of to find the size of an object. Most objects take up 1 byte of memory. A single object may use 1, 2, 3, 1, 2, 4, 8, or even more consecutive memory addresses. Basically, not basically, because we type out memory through variable names, the compiler is able to hide the details of how many bytes a given object uses. We can access some variable of x. The compiler knows how many bytes, Even so, there are several reasons it can be useful to know how much memory an object uses. First, more memory an object uses, the more information, it can hold. So we're finished with the void types. And now we're on to object sizes and the size of operator. Okay. There are several reasons. First, the more memory a object uses, the more it can hold. A single bit can hold 2 possible values. Okay, I did not actually know this. So we're still in first. A single bit can only hold 2 possible values, a 0 or a 1. 2 bits can hold 4 possible values. What is the best way to do that? So bit 0, 0, 1, maybe like that. Can hold 4 possible values. Can hold 4 possible values. Maybe if we did that. And then we did bit 0. And then we did 0, 0, 1, 1. And then we copied that, but we did bit 1. Bit 1 can hold 0, 1, 0, 1. 3 bits can hold 8. So it goes 2, 4, 8, and 16. No, okay, 8. But there is something called 16-bit, right? 16-bit. Yeah, I thought that was. Okay. 3 bits can hold 8 possible values. And then we'll just copy and paste that. So bit 2. So bit 0 with 3 bits is, so 1, 2, 3, 4. 4 zeros and 4 ones. 1, 2, 3, 4. 1, 1, 1, 4. 1, 2, 3, 4. And then bit 1 is 0, 0, 1. 2 zeros, a 1, a 1, another 2 zeros, and then another 2 ones. Whereas bit 2, sorry, is 0, 1, 0, 0, 1, 0. Okay, so it's 0, 1, 0, 1, 0, 1. 0, 1, 0, 1, 0, 1, 0, 1. To generalize, that's very useful to know and to make note of. Okay. Right. Where was I? Yeah. So it's 2 to the power of n. So 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. Yeah, so 8. And I assume 4 bits is 2 to the power of 4, which is 16. So that's the first bit. Second, computers have a finite amount of free memory, yes. And every time we define an object, a small proportion of that free memory is used. Modern computers have a lot of memory. However, for programs that need a large amount, the difference between using 1 byte and 8 is significant. Yes. Fundamental data types. Instead, the standard says the following. An object must occupy at least 1 byte, so each object has a distinct memory. A byte must be at least 8 bits. The integers char, short, int, long, long have maximum size of 8, 16, 16, 32, and 64 bits, respectively. So long has 2 to the power of 64. Char and char 8t with the suffix of t are exactly 1 byte. At least 8 bits. Oh, so a byte. Yeah. A byte is 8 bits. Fundamental data types. Types. That's interesting to know. So an object must occupy at least 1 byte. Byte rather than bits. A byte must be at least 8 bits. And then, okay. Okay. So a byte is made up of 8 bits, and 8 bits is 2 to the power of 8, and 2 to the power of 8. How do I do? Yeah, 2 to the power of 8 is 256. In this tutorial, a byte other interesting facts. A byte is 8 bits. Memory byte, addressable, floating point, and then we are in okay. So a Boolean is maximum size is 1 byte, typical size is 1 byte, and a byte is 8 bits. So I know we copy and paste, but I find that if I write something down myself, it goes in a lot easier. So a byte is made up of 8 bits. Yes, we're still good. What is the best way to do that? I think potentially taking a screenshot rather than copying it. Yeah, so I've got that for future references. So a long is 8 bytes. Minimum size, typical size. So a long is an integer or an integral type. And it's 8 bytes, which means that it's 64 bits, right? 8 bytes is equal to 64 bits. Yes. Yes. Because 8 times 8 is 64. Size of operator. In order to determine the data type, the size of it, we can use a size of operator. Yes, we covered that briefly. So let's get rid of that. We'll then do the size of operator. And then in order to determine the size of a data type, we can use the C++ provided operator of size of, which we covered in previous lessons. I don't remember the exact lesson, but maybe one of the first, 1.2 or 1.4 or something. You can compile the following program and see how large the data is. Okay, so we're using some built-in libraries that I've never seen before for C++. So we're including iomain p. We've already got iostream, and we've got climits, or I assume climits. So IO is a library used to manage input and output formatting. Okay. And it was input output manipulation. This allows access to tools such as setW, set precision, and set fill. Okay, we can then also use climits. So what is in C++? No, that doesn't help at all. The header defines constants with the limits of fundamental. Okay, yeah, so that refers, I assume, back to this, i.e. the limit of their size. Okay. We can also use the library of include climits, which is part of the C program. Yeah. Okay. So what we're doing now is we will copy out that. So the C limits is for char bit, and the char bit seems to just say so. Yeah, as I thought, that just relates to the size set W. What is set W again? Set W uh, sets the minimum field for the next input or output item. Set precision sets the decimal precision for floating point numbers. Set fill sets the padding character used to empty fill spaces. And set base sets a number base for integral values. I think that would be useful to copy. But that needs to go above that. I think what I'll do now is I will take a break, a short 5 minute break. So I'll be back in a minute just to go back over this. So a boolean is one byte. So long, I assume. So set W does what again? Sets the minimum field width for the next input or output item, which it relates to this, i.e. width, that means size. Trying size of an incomplete will result in, okay. Okay, I'll take a break here and I'll be back in a minute. All right. Okay. Let's continue. How are we looking? We still Gucci? Yeah, seems like it. Um, uh, where are we then? We are here, and let's continue then. Okay, so where were we? Bytes, and using size of on voids. And remember that void, uh, if you're using void as a parameter, you may as well not use it at all. Okay, so you can use size of operator on a variable name. Right, let's give that a go. How are we looking for the time? 12:30. Okay, so we'll probably go for maybe another hour with a break in between. So let's push forward on this. So let's close that. We'll do include IO stream, and then we'll do an int of main with a unassigned integer, and then we'll have an initialized integer. Then we have an std character output of x is, and then we will have user size of x, and then space bytes, and then a new line break, and then return. Return 0. So if we run this code, x is 4 bytes, which means that it is 24 bits. No, 32 bits. I would say, well, yeah, because 4 times 8 is 32, no? Yeah, 32. Okay, good. At least I know basic maths. That's always helpful. X is 4 bytes, and x is 4 bytes. Cool. On modern machines, objects. Okay. Singed integer. Am I saying that right? Sing. Sign. No, signed. Signed integers. My bad. No, I'm not going on holiday yet. Signed integers. Integers. An integer is an integral type that can represent positive and negative numbers, whole numbers. 4 primary integer types are available. So we'll copy and paste that. Do that here. We will then, what's the best way to do this? We'll probably just do type min size and then any notes, and then we'll split them with this, probably best. Short int int, long int, long int, min size, again 1, 2, 3, min size 16 bits, which is 2 bytes, 16 bits, which again is 2 bytes. I just want to make a note of that actually. 2 bytes, 2 bytes, 32 bits, which would be 4 bytes, 4 bytes, and then 64 bits would be 8 bytes. And then 1, 2, 3, nothing here. Just do empty. Nothing here. Sorry, integer is the one with the typically 32 bits, which would be 4 bytes on modern architectures, and then the rest are empty. And then I think just for reference, I will screenshot that. The key difference between various integer types is that they have varying size. The larger integer types can hold a bigger number. Signed integers. When writing negative numbers in everyday, we use a negative sign. Signed, yeah, so it was signed, not singed. We typically recognize +3 as +3. For example, being positive, negative, or 0 is called a sign. By default, integers in C++ are signed. Therefore, they can be positive and negative. And also 0. In this lesson, we'll focus on signed integers. So, defining signed integers. Here, this is the preferred way of defining the 4 types of signed integers. Signed integers. 1, 2, 3, 4. So short S, int I, long, okay, yeah, that makes sense, long, and then long, L, L. Although short int, and long int will work, we prefer these short names. Yeah, in addition to being more typing, adding the suffix makes it hardest to distinguish. The integer types can also take an optional signed keyword, uh, which by convention is typically placed by the name. Prefer short, do not use that. Okay, that does make sense. So that was just the syntax of that. As you learned in the last section, a variable with n bits can hold 2 to the n. Yes. Range. For example, an 8-bit signed integer has a range. Okay. So it's the assigned integer. Right. So the signed integers have a range to them. So an 8-bit signed, and then a 16-bit signed, and then a 32-bit signed, and then a 64-bit signed. Sorry if I'm going a bit non-verbal, but I'm just trying to understand this. The range and then we'll probably do it in brackets, to be honest. So that, and that, and then I'll just copy that. Because 2 to the power of 2 to the power of 8 is 128. No. Okay, so it doesn't relate to that at all. The range 16-bit is that. And then 64-bit is this. So I assume anything above 64 is just above that. Oh yeah, because it's 2 to the power of n. For the math inclined, sign variable has a range of that. Yeah, exactly. For the non-maths inclined, use the table. Overflow. Okay, what is overflow? Overflow happens when we assign the value 140 to an 8-bit integer. So an 8-bit integer can only hold -1 to 8. Actually, I just want to not copy and paste, screenshot this, just in case I don't understand the table in the future. So an overflow is when we have an 8-bit, when we try to assign an integer of a value of 140 to an 8-bit signed integer, i.e. we try to assign 140 to something that only has 8 bytes. For example, I assume a character. The number is outside the range that is the 8-bit. This is called an overflow. So I will copy and paste that. Therefore, assigning 140 to an 8-bit integer, 8-bit signed integer, will result in undefined behavior. If an arithmetic operation, such as an addition or multiplication, attempts to create a value outside the range, it can be called integer overflow or arithmetic overflow. For signed integers, integer overflow will result in an undefined behavior. So here we have our return type of integer in our main function. We assume 4 bytes because we're using integer. An integer is 16 bytes. Sorry, 16 bits. And a byte is 16 bits, and a byte is 8 bits. So but we're using bits, not bytes. We assume a 4-byte integer, and 4 bytes is 32 bits. Assume 4-byte integers. Oh, sorry, my bad. Assume, Assume, i.e. we're creating a 4-byte integer, which is 32 bits. The maximum value of a 4-byte integer, yes, which is this. Yes, that makes sense. Which is 32 bits, yes. Standard character X. The machine prints, however, the second output results in undefined behavior. The value may vary on your machine. Okay, because we've gone over this. Okay, that makes sense. We've gone over the 32-bit. So we've gone over the 32-bit. Well, we haven't here, but we've gone over it by adding 1 here. Okay, that makes sense. However, because the second output, let's give that a go actually. No, I don't want to save the website. Let's give that a go. So we'll do include IOStream. We have an integer of main. We'll then initialize our x variable to be 32 bits, aka 4 bytes. So we'll do int x and int x, and we shall do Okay, so we're not allowed to do, we have to do single quotation marks. I did not know that. 2, 1, 4, 7, 4, 8, 3, 6, 4, 6, 4, 7. And then add some spacing in between that. This is the max value for 32 bits, aka 4 bytes. And then we will print X with a line break. Cool, with a line break. Then what we'll do is we will do X equals X plus 1, and then we will put X with a line break as well. And then we will, as always, return 0. So let's give that a go. Let's clear our terminal. Let's run it. And we still get that. In general, overflow information. Yeah, so even though we've added 1, we've actually got an undefined value here. Which means we've actually lost data. In general, overflow results in information being lost. So that would mean then in that case, we would do this instead without looking further. Would we do that? Not clear. If we do long int, because we know from previous, we do int long. We don't need int, we just need long. Correct? We'll run it. Cool, nice. So getting the hang of it a bit. Integer division. How we looked on time. I think I'll just take a short break here and then we'll do the final roughly half an hour when I get back. Yeah? Cool. I'll be right back. Okay, and we're back. And we're looking, let me just so that displays all good. Cool. Okay, and then the computers are logged in. Yeah, the laptop, I mean. So let's keep trucking forward. Right. Let's keep going. So integer division. So it's very good that I noticed that. So that's good. At least I'm learning. Right. Integer division. So this is where knowing the syntax of int long, no, sorry, it goes short I int I, no, sorry, s long, and then long comes into play, and comes into play. Okay, integer division. Okay, when dividing two integers in C, you'd like to expect when the quotient as a whole number. 20 divided by 4 should produce 5. But look what happens when an integer division causes a fractional result. So let's give that a go. We'll get rid of this. We'll include we shall include what do we want to include? IOStream, and then we'll do int main, and then we'll do std character output, and then we'll do 5 divided by 8, and then we'll do that, and then we'll return 0. Let's see what happens. 0. No, because it's 5 divided by 8, not 8 divided by 5. Let me clear that. Let me clear that. And we get 1. I assume that means because it's the rounding, no? When doing division of two integers called integer division, C++ always produces an integer result, i.e. because it cannot, I remember in the first episode or first lesson we did, it was something called narrowing. Yeah, since integers cannot hold fractional values. Yeah. Any fraction proportion is simply dropped, not rounded, i.e. narrowed, I believe was the word that was used by this guy. Okay. Taking a closer look, 8 divided by 5 is 1.6. The fraction is dropped. 8 divided by 3 equals 1, remainder 3. Yeah. Be careful when using integers. So that would be when we would use a double. So what would be the range of a 5-bit signed integer? A 5-bit signed integer is within the range of, no, sorry, a 5-bit signed integer would be 2 to the power of 5, which is 32. No, that's 32 bits. 32 bytes. So it would just be 32, whatever 32 bytes is, wouldn't it? 2,147,000, 2,147,483,648 to minus 2,147,483,648. Sorry, are we doing, sorry, is it bits or bytes? 5-bit. Oh, then it would just be 132. It'd be the same. Am I tripping here? Okay, so it's just going back to this, and I was just getting confused. So where am I? So a 5-bit can support two. So I was right in that. Um, I was right in that. Uh, are we down? How's the? Hang on. It looks like the stream's down a bit. Let me just sorry. Just a second. Getting a bit of a bug here. Let me just test my audio. Hello, hello. So on my software, it's fine. What about on YouTube? Okay, so we're all good on YouTube and we're all good on my software. So let's continue and hopefully there we go. The error's now disappeared. Okay. So where were we? Yeah. So a 5-bit integer. A 5-bit integer would be 32 because you're dealing with you're doing with 2 to the power of n. So it was just 32 like I did there, but I was just getting confused with bits and bytes. For a signed integer, yes, because a bit is different to a byte, but essentially 2 to the power of 8 is 128. It is not, it is 256. So the range would be, no, it's because I skipped over this bit, isn't it? Uh, so 2 to the power of n, the nth integer has a range of minus 2 to the power of n minus 1. So 2 to the power of 5 minus 1, so it ends up becoming 2 to the power of 4. And then 2 to the power of n minus 1 minus 1. So it ends up becoming 2 to the power of 5 minus 1 being 2 to the power of 4. And 2 to the power of 4 is 16 minus 1. Okay, I definitely need to make a note of that. I don't think I need that. So signed integers range. So the formula for the range that a bit can hold is this, i.e. 5 bits can hold and that didn't copy and paste. So 5 bits can hold 5 bits can hold that. So it would be minus 2 to the power of 2 to the power of 5 minus 1 to 2 to the power of 5 minus 1 minus 1, which is then, so 2 to the power of 5 minus 1 is 2 to the power of 4, to 2 to the power of 4 minus 1, and then 2 to the power of 4 is 16, so minus 16 to 15, right? Yes. Okay. What is the result of 13 divided by 15? That would just be 2, wouldn't it? Yes. And what is the result? Minus 2. Yeah. Cool. Okay. Let's carry on with that then. Close that. And we'll go on to unsigned integers and why to avoid them. So now if we do unsigned integers, unsigned integers. A set of types that can hold positive and negative numbers, including 0. And then yes, unsigned integers are integers that can only hold non-negative numbers. Non-negative numbers. So unsigned integers. Integers are integers that can only hold non-negative whole numbers. Cool. Defining unsigned. Oh, so you literally do unsigned. As the key word. By convention, this was placed before the type. So you got unsigned, unsigned short, unsigned int, and unsigned long, and unsigned long. Unsigned integer range. A 1 byte unsigned integer has a range of 0 to 255 because a byte is 8 bytes. A byte is 8 bytes. 1 byte is 8 bytes. Yes. No, that's wrong. Compared to this 1 byte integer range, both can store 256 values, but signed values have half the range because they can only store non-negative numbers. Okay. Okay. Here's a table showing the range of unsigned integers. An n-bit unassigned variable has a range of. Okay, so unassigned variables have the formula of, or have the range of 0 to 2 to the power of n minus 1. Okay. So it's always 2 to the power of n. Okay. Always 2 to the power of n. Sorry, I'm just making sure that my my audio is all good. Sorry. When no negative numbers are required, unsigned integers are well suited, but you never actually know, really, do you? Because unsigned integers can be stored more positive without taking numbers. The following is a simple way of remembering the difference in order to differentiate the different negative numbers. If a sign is not provided, we assume the number is positive. Okay, that makes sense. So does that mean we always have to use signed? No, doesn't, because like we learnt here, or wherever we learnt it, we can just do this and that assumes that it's signed. Whereas if we did unsigned, then that would cut the range in basically half. So we just assume that it is signed. Okay. Apologies, just a second. Yeah. Okay, so let me just get that. Okay. What's the time now? Okay, how long we got left on this? Oh, quite a bit. I think what we'll do is we will go until 1:30, so another 15 minutes, and then I think we'll call it a day. Okay, let's continue. Yeah, what happens if we try to store the number 280 in a 1-bit in an 8-bit integer? The answer is overflow. So 280 is over the unassigned range. If an unassigned value is out of range, it is divided by 1 greater than the largest number. Only the remainder is kept. The 280 is too big to fit in our 1-bit range, yes. Therefore, we divide 280 by 256, getting the remainder of, getting one remainder 24. The remainder 24 is what is stored. Here's another way of thinking about it. Any number bigger than the range modulo, which can often be defined or used as this or represented as that. Where was I? However, 256 is out of range. So I think the best way to do it is just practice it, to be honest. So we'll do the same as that code. We'll do an int of main, and then we'll do unsigned short x by a short integral type, and we will do 6 5 5 3 5, which is the largest 16-bit possible. Then we will make x equal to 1 more than that. Or we could just do x plus 1. And then std character output. X is now, and then our x value. And then a line break. And then if we did x equals, again, x plus 1, and then we did standard character output, x is now x. And then we return that. So that means we should get x is now 0, x is now 1. And just to get the same result as him, we will do x was, and then x with a line break. And then we'll run. X was that. So basically it wraps the modulus around and gives us the integer. Okay. With unsigned integers, if we go out of the range, the number we are holding becomes the value of our remainder, or modulus. I think that's how you spell it. It is possible to wrap in another direction. It is possible to wrap the other direction as well. 0 is represented by 2 byte, which is 2 byte is 2 bytes is 4 bits. No? 2 bytes. 2 bytes. Oh, it's 6. Oh no, because it's the. Two bytes is 16 bits, yes, as per this. 16 bits. It's possible to wrap around the other direction. Okay, yeah, that does make sense. So we go from 0 and then we go to the upper range, uppermost range. The above code triggers a warning to the compilers. Okay, so you can go both ways. The controversy of unassigned numbers. What's the time? I'll go for another 10 minutes, see where we are, see where we end up. We might even finish in 10 minutes. Many developers and some development, such as Google, avoid unassigned. This is largely because two behaviors that can cause problems. First, so why unsigned numbers are avoided. First, with a signed number, it takes little work to accidentally overflow because the values are far from 0. With unsigned numbers, with signed numbers, it takes little work to accidentally overflow. With signed numbers, it's much easier to overflow. So you've got unassigned 2 and then 2 minus 1. Unsigned 2 and 3. But then, okay, I see. So you got 2 and 3. 2 and 3 are within the range of a normal integer. However, of the 8-bit integer, and we know that an integer is we know that an integer is 16 bits, and the range for unsigned integers is 0 to that. Yes. So that means that if we did 3 minus 2, we would get -1, which would then print that. Yeah, which is the which is that because it overflows onto the next uh onto the next range. Yes, that makes sense. Yes. Secondly, and more insidiously, unexpected behavior can result when you mix signed digits with unsigned integers. In C++, as one signed and unsigned, signed integer will be converted to unsigned. Okay. Second. Yes, which is why you still get that error. U is signed, unsigned. S gets converted from signed to unsigned. And again, this prints, this will change this to unsigned. And so S, if S is greater than U, which it, sorry, if S is less than U, which it is, standard character output that, else 1 is less than -1. But because we are using unsigned and we're comparing them, signed becomes this, which is why this executes. Yes. Okay. Consider the following. So we got assume the integer is 4 bytes, run the code, do something -1. So if it's 4 bytes, that means it's 32 bits. And then we will get that or that. The author of do something was expecting a mistake. The sign wraps around. Yeah, so I would assume it would go to 64 or the next bit. Yeah, sorry, it wouldn't go to 64. It would go to go to 33 bits. Let's give that a go actually. Let's see actually what happens because otherwise I'll never learn. So print. No. No. I understand now. Because our integer, our unassigned integer is 4 bits. Sorry, 4 bytes. Our unassigned integer is 4 bytes. Our unassigned integer is 4 bytes. and it's -1, which means it goes to the end range. But go away. 4, 2. Why is that the case then? What is the no, surely the reason why it's producing 32 bits is because an integer is 16 bits and our range is for unsigned is 0 to 65,000. Yes, that must be it. Our integer goes from our unsigned integer is 0, our range is 0 to 65,000. So when we go to 0, yeah, we jump to 32. Okay, that makes sense now. That does actually make sense. All these problems are commonly encountered. Best practice. Okay, good old best practice. Favor. So, the best practice when it comes to signed and unsigned integers is to favor signed numbers over unsigned, and avoid mixing. Yeah, that could be useful. So I'll just copy that. And I think we'll leave it with that. So we'll move on to the next lesson. So then we'll see how far we've got left. So we've done those 4 lessons and done that. So the fundamental types, as I'm bugging a bit. So we'll probably finish fundamental types tomorrow, depending on how long these are. We've already covered chars a bit. We've already covered floating points a bit. So we will off to just size with this lesson. I think in an exited, the website might be impacting it a bit. So our audio is going fine, but my 1, 2, 1, 2. Okay, good. We're back. So anyway, we'll leave off from there. We'll just save it in GitHub for now. Okay, so we're back. Good. We'll save it in GitHub for now, all the work we did. So day 6, part 2. Day 6, part 2. And we did, what did we do? We did signed and unsigned integers. We did the difference between bits and bytes. What else did we do? Fundamental data types. Void data types. Object size and size of operator. Signed, and then integers overflow. Cool. Tutto bene. And the date today is the 3rd? Yeah, 3rd. 3rd of the 8th, 2026. Okay, so we'll continue next with fixed width integers and size. If you follow along, well done. We're really starting to get, so we've just finished the debugging, so now we can move on to the more data types. And it looks like I was going to go on the website, but I don't want the stream or the video quality to go back down. But it looks like we're getting more into the nitty-gritty of coding and C++, and hopefully that can create really exciting projects. And I have got a few projects in mind when it comes to that in the future. Okay, so if you follow along, well done. Hope you're enjoying C++ as much as I am. Anything you saw that I did and you think I can improve, please comment on it. Anything you'd like me to do, please comment. And in general, if you're enjoying it, let me know. So please like, subscribe, and I'll see you in the next one. All right, bye.